So look at these questions here that I have here. These are more of the kind of stuff that I like for students to kind of like have a sense of. In other words, more the conceptual stuff. So the issue here is in your readings, you'll find these two symbols, right? You'll find both the delta G and delta G naught. And the idea is, what is the difference between them? Now, I would ask you to answer, but again, you can't participate. So, maybe a few seconds to think about that. And then we'll say that essentially, let me go back here to the other screen, which is a little easier to deal with. So what we're going to say is that delta G naught, I can't do the subscript right now, the symbols, is for standard conditions. So many times, as you'll see, they're the same, but typically delta G naught is typically established for 1 atmosphere pressure. The reactants in solution are at 1 molar concentrations, and the temperature typically is defined as 25 degrees Celsius. Now, as we know, as the chemical reaction progresses, right, from reactants to products, you lose those standard conditions because the concentrations are no longer the same. So that is where delta G goes. Now, when do we say that a reaction is spontaneous in the forward direction? What does delta G have to be? Negative, right? So it has to be less than 0 in order for it to be spontaneous. We said that's because that's what the second law of thermodynamics tells us, right? Now, what does it mean? What is the value of either delta G naught or delta G when the reaction is at equilibrium? So we said that's 0, right? And it's the same for both. Now, again, remember that whether we're talking about the regular delta G or the delta G naught, we are describing conditions essentially, right? Now, when is a reaction non-spontaneous? We said according to the second law of thermodynamics, a reaction is non-spontaneous, but remember, we always have to condition that or qualify it. We're talking about the reaction as written. Remember that many reactions are reversible, and it depends on which way you write it. You calculate delta G for the direction given from left to right. That's purely a convention. So if delta G naught is positive, it means the reaction is non-spontaneous. But this would be, again, like I said, under standard conditions, correct? Because we are saying, let me do something here, just do a little coloring here, so we know that this is something that I added. All right, remember that as the ratios of products and reactants change in a reaction, we had that Nernst equation. We'll study some equations where you'll see the different values of delta G as the ratios of products and reactants change with respect to what the standard conditions would be. So that's another little qualifier in there. Okay, so when are delta G naught and equals to delta G? So we're going to say what? When delta G is at standard conditions. Okay, so these are more conceptual things that I want you to remember always, right? So what I had for you was a little exercise. I was going to have you guys do this. So the idea here is a chemical reaction. And again, we always consider it in the direction that is written, correct? And you can see it there. So we have HCN reacting with oxygen to produce water, carbon dioxide, and nitrogen. Before you dig into any math, don't forget, first get a sense of what's going to happen. For example, just by looking at this equation, can you get an estimate as to whether delta S is going to be positive or negative? And why is that? Can you get an estimate as to whether it is positive or negative and why? How do you answer that? What do you look at?
Are we looking at the moles on the product and reactant side?
Moles of what? Specifically.
I'm gonna say product side.
Yeah, but
If it's more or less.
yeah, but moles specifically of what? Gases, right? Gases typically, gas changes typically, we're going to say drive entropy changes because the entropy of a gas is so say so high. So we look here in this case, we have on the left side, we have how many moles of gases? We have the 5 oxygens, right? Because the HCN is liquid. So we have 5 moles. And then on the right side, oops, you have 2 of water, 4 of CO2, and 2 of nitrogen. So that's 8 moles. So since you are increasing the numbers of moles of gas, you predict that, that entropy will increase. In other words, delta S should be positive. See? So that's one of the things you look for. You look for 2 major things. Is there a change in physical state from, let's say, solid to liquid or liquid to gas? And if there are gas reactants and or products, how does the number of moles of gas change? Because they're going to drive the whole entropy process. The entropy of gases is huge in comparison to liquids and solids. Remember that if there is no net change in the numbers of moles of gas, you're really not going to be able to predict just from looking at the equation whether the entropy is going to increase or not. It's going to be, it may be positive, it may be negative, but it is likely to be a very small number, small value. Okay? Let me know if you have any questions. Let me see if I can, gosh, I can't move this thing around too well. Okay, very good. So Dixie, you had that, the gas ratio, very good. Good job. Okay, let's look at this other one here. So in the next question here, I'm going to give you a table. What you're going to do is you are going to show, here we go. I honestly don't know if you guys are seeing what I'm seeing. Let me know. So we're going to go to the next question here. Okay, so now we have the same equation, same reaction. And this is typical of these kind of questions. They give you a table of values. So this is to calculate delta S using the table provided. And now you get to ask, oops, is the result consistent with your expectations? Is the result consistent with your expectations? I'm looking my cursor? I can't find it. Okay. So again, the idea here is, I don't know if you remember how to do this, whenever they ask you to calculate a change in some kind of thermodynamic property, they're typically going to give you either the standard entropies or the standard enthalpies or the standard free energies. Again, remember that since they're giving you the entropies here, go back here to the slide. I totally lost, I'm losing my cursor every time I move around here. Can't find it. I'm sorry guys, I'm losing my cursor here. Here we go. So in this case, what they're giving us is, we're going to look for this value here. All right, we are looking for the standard entropy. And remember that essentially the delta S for the reaction is going to be the summation of all the entropies of products minus the summation of the entropies of the reactants. Sorry, but my slideshow is projecting onto my side screen, and I don't have. It's not a touch screen. I was trying to do it on the other one, but I can't make the slideshow show up on my regular laptop. So essentially, that's what you're going to do. So remember that the entropies are given per mole. So you have to be careful about considering the coefficients. Obviously, you need to make sure that the equation was balanced to begin with. We're hoping that it was. Hoping that it didn't trick us on that one. Correct? So let's go back. I'm going to come back here to our to the actual file here because I think I can write in there. Okay, here we are. So again, let me move this table out of the way here. Okay, so we have delta S of products. So we have water, right? So that'd be 2 times the entropy of water, which is 189, plus 4 times the entropy of CO2, which is 214, plus, oops, sorry, that was 4, plus 2 times the entropy of nitrogen, which is 192. Remember that as opposed to enthalpy, delta H, you know, where the heat of formation of an element in its standard form is 0, you can see it there for oxygen and for nitrogen. The entropy is always bigger than 0, because remember that the entropy is only 0 according to the third law when you have a perfectly constituted crystal at absolute 0 of temperature. All right, so now we're going to subtract the reactants. So it'll be 4 times the heat of the entropy of HCN, which is 94.1. And we're going to have 5 times the entropy of oxygen, which is 205. Close the bracket there, and the rest will be just numbers here, right? So, sorry, I have a very cheapo calculator, so I have to do it almost by hand. So 94.1 times 4, and then we have 205 times 5. Okay, so that's 1,401. Then for the other one, it was 2 times 189, 4 times 214, 2 times 192. That gives me, I have 1,618. So that minus 1401.4 equals 216.6. Well, technically, since the first group here doesn't have any decimals, we round that to 217, and this would be joules per Kelvin per mole. You guys, hopefully you guys got the same. Did you guys get that? Same one. Okay, so does that corroborate our initial assumption, which was that this should give us a positive value? So we'll say yes, the result is, whoops, what happened here? Result is consistent. Delta S is positive. That's what we have predicted before. And see, these are the kinds of things you do when you're looking at these problems is don't just plunge into the math blindly and just get whatever. Think about, does the result I'm getting make sense? Okay? All right. Let's do the next one here. Let's see. All right. Got it. Okay, let's go to the next one here then. So the next question I'm going to have is, as you can expect, I'm having a really hard time with this screen sharing here. Just not being able to share the screen appropriately here. Okay, so this is what we had. And now we're going to go to the next one. So the next question then is, same as before, you're going to calculate delta H using the table provided. And again, this time, so we're going to be looking at this area here. Again, don't forget that in the case of enthalpies, the enthalpies of pure elements in their standard form is 0. So if instead of oxygen like this, it would be, let's say, for example, it would be ozone, O3, that number would not be 0. Right? If this were, let's say, instead of N2 nitrogen, it would be N, like monatomic nitrogen, that number would not be 0 either. But again, same thing again, this is going to be essentially the summation, right, of the delta H's. And remember, these are delta H of formation. I explained in the lecture, just a review from Chem 1A, that what we're doing essentially is we are assuming, or we're inventing a path for this so that we can kind of calculate what's important, which is the end and the beginning. And because these are what are called properties of state, you don't care really how the reaction proceeds. You don't really care about the mechanism of the reaction itself, because all you care is where did you start and where did you finish. And as long as you have the correct starting and finishing points, we should be okay. I'm going to give you a few seconds and you can do that yourselves. I don't have the answer with me, but I'll let you do that. I'll give you a few seconds to work on that. And same as before, be careful with the coefficients, like of these things. Obviously, in this case, we don't really care about the oxygen and we don't really care about the nitrogen because those are going to be zero. So it's only the water and the CO2 and the HCN. Don't forget, if you are looking at these numbers in a regular table, like not as specific as this one, where they give you exactly the values for the species involved. If you were to look, for example, in the Tro book in appendix, I forget 2 or 3, wherever the thermodynamic constants are, you have to be careful, for example, that you choose the delta H for water gas, for steam, not for water liquid or ice, water solid. Make sure you find the value for that specific physical state. All right, I'm gonna let you guys do that. I'm not gonna work it out. This should be this just at this point becomes a math problem. But what I want to do is, well, let me give you a few more seconds. You should be able to do that very quickly. And again, remember when you take the quiz, you're gonna have a similar question to this one. The key thing is practice a lot so that once you see the question, you know exactly where to go to and you don't waste time kind of like looking around, looking in your book. How do I do this? How do I do that? Because remember that your 20-minute or whatever allocation of time includes the time to upload your answers, right? So don't get caught in, messing around trying to find how to do something. If you practice a lot, you'll get a quicker skills and you'll be able to go to the solution a little quicker. Okay, I'm gonna go ahead and jump to the next one. I don't have the values here. I'm gonna let you figure it out. If you want later on, I can post an actual file with the total answers. I'm just trying to walk you through the procedures here. Okay, so let's see. Find my cursor. There we go. Okay, so let's ask the question. I guess the question we're going to ask here is, under what conditions would this reaction be spontaneous? Now, I haven't done delta H from this previous one, right? But just so you know, when you calculate it, you're going to get, well, let me ask you this. What do you think the delta H is going to be like? You think it's going to be negative or positive? Just looking at what kind of reaction this is. A reaction between a carbon compound and oxygen, producing water and CO2. What kind of reaction is that typically? Remember? Looks like a combustion. And combustions, we know that are typically exothermic. So this is going to be something I'm going to predict it. Now I'm going to let you guys do the calculation. I don't have the numbers here because I just picked this up like a few minutes before we started, so I'm sorry about that. So I'm going to predict that delta H is negative because this looks like a combustion reaction. So when you do the calculations, I don't know if you guys did it already, but that's what you should get. And let's see now, based on these values, what do you think will happen? Will the reaction be spontaneous, given the delta S value from number 2 and from number 3? Now remember, let me go switch again here. Let's go back to our thing here. Okay, remember that ultimately what we have is, and again, I don't have the ability to do here, but delta G equals delta H minus T times delta S, right? And here is this table. Let me go back to the table over here. Switch over here again. This is so bad I can't. Here we go. Go back to the big screen here. So what I'm showing you is this table here, which is something you've seen in probably a different format in our lecture, but what it does here, it compares based on the value of delta H and the value of delta S, what would we expect for things to be? So we're looking at the value of delta H and the value of delta S. Now remember, in our case, we decided, or we found, right, that our value for delta S was positive, and our value for delta H, and we don't have the number itself, but we said that it was negative. And you can confirm that later on. So let's find that in here. So we're looking for a positive delta S and a negative delta H, and that's the answer you get. It's always spontaneous. Why is that? Well, because if delta H is negative and delta S is positive, remember the absolute temperature T, which is not Celsius but Kelvin, is always a positive number. So that means that if delta S here is positive, negative minus this is always going to give me a negative delta S. I mean, sorry, a negative delta G. This is just pure math. Okay, we're not trying to construct any kind of physical or chemical analogy here. This is just math. If delta H is negative and delta S is positive, you have a net negative delta G, which according to the second law tells us that the reaction is spontaneous in the direction given at any temperature. Notice that there's other scenarios where things would have been different had the conditions been different. All right, cool. Okay, so let's go to the next one then. And this will be the last question here. What will be delta G at 20 degrees using the delta S that we got in number 2 and the delta H from number 3? And I just realized I forgot I don't have the number for delta H, but we already gave you what the way you answer this, correct? Is you are going to go and you're going to say, well, delta G, and notice that this doesn't have the little naught, the little subscript little 0, because, I hope my audio is not fading out here, I'm sorry. Sometimes when I switch this around, this cheapo mic doesn't pick up the sound very well, but hopefully it will. This is not at standard conditions, so we're going to say delta G is going to be delta H minus T times delta S. Now don't forget, this temperature here is not Celsius. This would be the Kelvin temperature. And you don't have to memorize this, because in an exam I will give you these conversions. But you obtain the absolute temperature by adding 273.15 to the Celsius temperature. Oops, sorry. Put that parenthesis in the wrong place. And this would be the temperature in Kelvin. That's the one you want to use. Don't forget. Let me see if I can fix this a little bit here. Here and put this parenthesis where it belongs. There we go. So again, you have this delta S. You'll get that value from there, and then delta H, you'll get it from there. Don't forget that your delta S was in joules, and your delta H was in kilojoules. So don't forget to convert the units either all to kilojoules, which is the preferred way for delta G. So we want to convert the entropy change, we want to convert it into kilojoules. So you can perform this operation here. And you'll have the temperatures will cancel out, but you'll still end up in units of kilojoules per mole. In an exam situation or quiz, I would probably tell you what are the units that we want to show in here. So this will be kilojoules per mole. Again, I don't have we didn't do the delta H, so probably what I'll do is I'll post this PowerPoint in your Canvas and show you the actual answers. I just wanted to walk you through the steps here. So essentially, that is the way these kind of problems work. You're given a reaction. The first thing you want to do is make an observation as to, can I predict what is going to be the sign on the entropy change, the delta S? That's one of them. Another one is this a reaction that I recognize as usually being exothermic or endothermic? That's not always going to be so easy, but there's some that are fairly obvious. And so you can make some preliminary predictions so that when you do the math, you look at the numbers and you ask yourself, do these numbers make sense? It's not just math. This is not a math class. Do they make sense in terms of, in the context of the topic we're studying, which is the reaction spontaneous or not? Don't forget a couple of other things. And what I'm going to do on our Thursday session is I'm going to do a wrap up review of all of our thermochemistry stuff, but it's going to be more conceptual than math. I want us to get these ideas. To me, it's more important that you understand these concepts and how they apply to different situations versus simply plugging numbers into an equation and doing math, which I know you guys can do. Okay. Okay, let me give you a few more seconds if you want to write that down, and then we'll come back and I will stop the recording at this point. And Dixie and Heidi, if you have any questions, I'll come back in one second.
Hey, Professor.
Yes.
For number 3, for the delta H, do you actually have an answer for that? Because I worked it out. I just wanted to check to see if mine was right.
You know what? I don't. What did you get?
Negative 2,662.
Negative 2662?
62, yeah.
No, I don't have the answer. But hey, let's go ahead and write that down and see if that's what it is. Hold on a second. Let me go back there. Okay, so you are saying that, let's see, are we seeing this one or are we seeing the big, which one are we seeing? Hold on a second. I haven't clicked the share button. Hey, sorry.
Should be number 3, I think.
Okay, so we got calculated minus 2662, is that what you said? So what you got?
Yeah, that's what I got.
Kilojoules per mole. Yeah, I mean, I don't have the numbers, but I trust that you knew what you were doing, right? So that means that we can go back here and plug that into that last one that we did. Let's see. So we would have delta G would be negative 2662. That would be kilojoules per mole minus 20 plus 273.15 times, what was the entropy that we had calculated before? What did we say it was? I can't see it here because I 217. 217, this would be joules per mole Kelvin, but we have to convert that to kilojoules. So 1 kilojoule is 1,000 joules. And so let's see what we get. Oops, sorry, I put small j here. This should be a capital J. All right, so we have 15. Oops, sorry. Plus 273.15 times 217 divided by 1,000. And then you have 2662 minus that. So I'm getting negative 2726 kilojoules per mole. Is that what you guys are getting? Thank you, Aini, for doing that calculation. We can check it later and embed it again. But so again, your quiz this week will be something similar. It'll probably have a reaction. They're gonna ask you to, well, whatever question they ask you is probably gonna require that you do these types of calculations of, delta G or whatever. Except that in that case, it may, this question was a little easier because we had a negative delta H and a positive delta S. In some of the scenarios that we've talked about, let me go back here. Remember that you could have a scenario where the reaction is only spontaneous under certain critical temperatures. Some authors call it the critical temperature. I don't like to call it critical temperature because when you study transitions of physical states, there's something specifically called the critical pressure and critical temperature. So I don't like to use that phrase. So I just call it, the temperature above which the reaction is or not spontaneous or whatever. So be aware of that. So that's the one thing I don't have a practice for. I'm sorry, yeah?
Sorry. It seems like Dixie also got the same number, but she actually, or he, I'm not sure, sorry, has the answer in positive 2,662. If that were the case, then our answer for number 4 would just be different, right? It would be only spontaneous
That's
above
correct, but
critical temperature.
It shouldn't be positive for delta H. Look at the products. See how all the products are negatives? Right? You can see them here. H2O is minus 242. CO2 is minus 393.5. Those are negatives. And then you're going to subtract the one from HCN. So it'll be a negative again. So it should be negative, Dixie. Make sure you put these as negatives when you put them into your calculator. Go back and check. Oh, you got it? All right. Looks like Dixie got it. Sorry, Dixie. I don't know very well how to switch between the chat and the regular voice. Okay. So let's stop the share here, and I am going to end the recording.